Okay, here we go. Today's lecture, please don't worry too much about details. If you're interested in the details, by all means, try stuff, work stuff out, come talk to me. But don't worry about the details. Just get the big picture, and I'll try to sum that up a few times. But yeah, there's a lot more detail that I put in these slides that you don't actually need to know. Okay, the only point of this lecture is to motivate the rest of the course. Okay, to tell you what the two pieces of the course really are. Okay, the area problem and the tangent problem. Calculus has two branches, integral calculus and differential calculus. Each one has associated with it a tool, integral calculus the integral, differential calculus the derivative. And each of those kind of arises naturally by trying to solve a particular kind of problem. The integral is to solve the area problem, and the derivative is to solve the tangent problem. And let's go look at what those problems are. So the area problem. What is the area of a circle with radius r? Someone want to say it? Pi r squared. Excellent. And we're going to see how you can figure that out. The problem with a circle is that it's curvy, right? And curvy things, it's hard to get their areas. And that's something we're going to come across later on as well. For a triangle, it's just half base times height. For a rectangle, it's just length times width. But for something curvy, it gets a bit trickier. So what can we do to get the area of this thing? Well, one thing we can do is approximate it. So we inscribe in it a regular hexagon, let's say, and we get the area of the regular hexagon, okay? And it looks close, right? The area of the hexagon should be close to the area of the circle, and the error in that approximation is all the stuff you're missing, these little slivers there, right? And it turns out that the area of the regular hexagon inscribed in a circle of radius r is given by 3 root 3 over 2 r squared. Now how can I figure that out? Or how did I figure that out? What you can do is you can split the hexagon up into 6 equilateral triangles. You can get each of their areas and sum those areas up. And again, this is that kind of detail that I'm talking about. You don't really need to worry about this right now, but if you're interested, please do. You can use either trigonometry or geometry in the Pythagorean theorem to figure out those distances. And from those distances, you can get that the area of each of the equilateral triangles is root 3 over 4 r squared. You multiply by 6 to get the area of the hexagon, and that is indeed 3 root 3 over 2 r squared. Okay? And that's a first approximation of the area of the circle. Now you could have done a worse approximation. You could use the triangle and stuck a triangle in there, in which case those gaps would have been bigger, right? Or you could do a bit better and do a square or a pentagon, but I thought a hexagon was nice looking and looked reasonably close to the circle. But again, you can do better than that, right? You can stick an octagon in there and get the area of that and use that as an approximation. And with similar methods, you can get that the area of the inscribed octagon is 2 root 2 r squared. Cool? And you'll notice both of those have an r squared in them. Okay? And I'm going to be mentioning that a few more times. Again, more detail. In general, the area of a regular n-sided polygon inscribed in a circle of radius r is given by that. And that isn't that hard to prove. Okay? So if you know some trig and just a tiny bit of geometry, you can figure that out. Okay? And I've written some of the quantities on there that would help you in figuring that out. And again, it's the same deal. You just slice the thing up into isosceles triangles, get the area of each triangle, multiply by n, and you've got the area of the pentagon. Of the polygon. And the idea here is that, okay, we did well with a hexagon, we did better with an octagon. As we increase the number of sides, we get closer and closer to the area of the circle, right? These discrepancies get smaller and smaller and smaller, and we get closer to the value we actually want, okay? And as we increase the number of sides, we can get as close as we want to the true area of the circle. And this demonstrates that, right? You can see by the time we get to 50 and 100 sides, you can't even see the difference between them in this picture, okay? Between the approximation and the actual area. In all the cases, the area is going to be proportional to r squared. It's going to be some number times r squared, okay? No matter how many sides the polygon has. And that suggests that the area of the circle should also be proportional to r squared, okay? And that isn't a crazy thing to believe, right? Area is a measure of two-dimensional size, so it makes sense for it to scale with the square of one-dimensional size, right? And when you talk about volumes, it makes sense for volumes to scale with the cube of one-dimensional size. Okay, so the fact that there's an r squared here shouldn't be that surprising. It's something that you're going to probably get used to. The constant of proportionality depends on how many sides that polygon has, okay? And as we get better and better and better, we get closer and closer and closer to the area of the circle, and you'll notice that that number is approaching a special number. again, the area of the inscribed regular polygon with n sides in the circle of radius r, its area is going to be proportional to r squared, no matter how many sides the polygon has. As we increase the number of sides, we get closer and closer to the area of the circle, and the constant of proportionality approaches pi. So that tells us that the area of a circle is going to be pi r squared. Does that make sense? Okay. Please say if you have questions, okay? And again, this is just that constant of proportionality, and this is the number of sides of the polygon we stick inside the circle, and you can see that that's getting closer and closer to pi all the time. Okay? Now you might go, well, that might not be pi. It might be pi plus 0.01 or something. How do we know it's actually pi? So one thing you can do is you can write out the area of the regular polygon, like so. So again, what do? You again split up the polygon into isosceles triangles. You can call the side length S, you can call the radius of the circle R, and this thing is called the apothem of the polygon, or it's the height of one of the triangles. And you can write out the area of this whole thing as n, because there are n triangles, times 1/2 base times height of each triangle. Okay? And you can rearrange that a tiny bit, and you can rewrite it as 1/2 times the perimeter times, again, the height of that triangle. Now you notice as the number of sides increases, that the perimeter of the polygon approaches the circumference of the circle, and that height of that triangle, or the apothem of the polygon, approaches the radius of the circle, right? As you get more and more sides, the circumference and the perimeter become indistinguishable, and the apothem and the radius become indistinguishable, right? So they get closer and closer together. Now on the last slide we found that the area of the polygon is 1/2 times the perimeter times the apothem. Now the perimeter is getting closer and closer to the circumference of the circle, which is 2 pi r. The apothem is getting closer and closer to the radius of the circle, which is r, right? 1/2 times 2 pi r times r is just pi r squared. Okay? So that should make it clear that the number is actually pi, and you're not being tricked by the graph being close to pi, but not actually pi. Another way you can see this is you can move around the slices in the polygon, and you can form a parallelogram or a trapezoid, and you can see what happens as you increase the number of sides. As you increase the number of sides, you'll see that, again, the polygon becomes a better and better approximation of the circle as these sort of bumps flatten out. And you'll see that the sides of this thing become more and more vertical. Okay? And as you keep going, you approach this kind of shape, right? A rectangle. Okay? And you can see where the side lengths of this rectangle come from. So these sides come from these sides. Okay? So each one is going to be 1/2 of the circumference. So each one is going to be pi r. And this side just comes from that height. And again, that's going to approach r as you increase the number of sides. Okay? So again, the area of this thing is going to approach pi r squared. Okay? Now again, there's detail there you don't need at all. But if you're curious, work it out or ask me. Do you have any questions about this so far? Okay. Now we inscribe polygons, but there's no real reason to do that. You could put them outside. You can circumscribe the polygon. Okay? And if you do that, you're going to be always bigger than the area of the circle, but you're again going to be approaching it as you increase the number of sides. Okay? So the inscribed polygon areas approach the true area from beneath, and the circumscribed polygons approach the true area from above. Okay? Both of them go to the same place, possibly at different rates. And if you do both of them, then you can sort of have an interval on which the true area lies. Okay, so you won't just have an approximation, you'll know that it's between those two values. And this whole method of increasing the number of sides to get the area of something like a circle is called the method of exhaustion. Okay, you exhaust the sort of possible space of areas that the actual circle can have as you converge like that. Okay, the integral is calculus's answer to the general area problem, right? When we want to get the areas of things that are curvy, we use the integral. And the way we're going to develop the integral later in this course is almost exactly like what we just talked about, okay? You build an approximating area, you split it up, and then you refine that approximation. You refine. And as you refine, you get closer and closer and closer to the true value, okay? And that's how you find out what the true value is. Okay, so again, the big picture I kept talking about was, what are you going to do? You approximate, you split things up, and then you refine your approximation and see where that takes you. Okay? And that's the area problem part. Any questions yet? Okay. The tangent problem. So if we know how an object's position changes over time, can we find out its velocity at a particular instant? So suppose the object is moving on a straight track so that one number is enough to tell us where it is. And suppose its motion is uniform, so it's always moving at the same velocity. Okay? Then its position versus time curve is just going to be a straight line. And its velocity at any instant is going to be the same as its average velocity over any interval of time. And that's just going to be given by the slope of that line. Okay? Rise over run. Okay? And rise over run in this case is the same as the change in position over the change in time. Okay? And that's just average velocity. The change in position or displacement divided by the change in time. Now, if the object is moving non-uniformly, you don't get a straight line anymore. You get something curvy. And again, curves cause trouble. So suppose you want the instantaneous velocity at the instant times 6 seconds. The way to do that is to draw a tangent to the curve. And that's called a tangent. You draw a tangent to the curve and you get the slope of that. And that should be reasonable, right? That this tangent is telling you essentially how steep this curve is here. Okay? If you zoom in far enough here, they'll look exactly the same. Okay? Or as close to the same as you want them to get. Does that make sense to everybody? That the tangent is a decent, is the best picture we have of the steepness of the curve at that point. Okay. And a tangent is something that essentially kisses the curve, right? If you zoom in far enough, it looks like the curve, and it only touches the curve once there locally. Okay, now the problem with a tangent is that you can't compute rise over run right there, because that's just a point, and you've got nothing to divide by, and you've got no rise, you've got no run. So what you can do is you can approximate the thing again. So let's get, instead of getting the instantaneous velocity here, let's approximate that by the average velocity from here to here. Okay? So what you do is you draw what's called the secant, and you get the slope of that. Okay? Essentially what you're doing is you're approximating the instantaneous velocity at that time by the average velocity over those 2 seconds. Does that make sense? Okay. Now, as we tighten up that interval, and as we get our average velocity approximates over tighter and tighter intervals of time, then we get better and better approximations of the actual instantaneous velocity, right? So instead of getting the secant from here to here and getting its slope, we can get the secant from here to here, tighter interval, and that's closer to the true tangent. I have a pointer, I could be using it. Or we could tighten it further, and further and further and further, and you notice that this secant, the dotted line, keeps getting closer and closer to the tangent, the solid line. Good? And so our average velocity becomes a better and better approximation of the true instantaneous velocity. And I mean, this should sound familiar, right? What did we do? We approximated something, and we made our approximation better and better and better, and then saw how that bettering took us somewhere. Okay? And that place it takes us is the correct answer, is the true instantaneous velocity. Does that make sense? Okay. And ask yourself why we actually need this. Again, this thing is curvy. You can't just take a slope. You can't just take a slope at a point. So what you have to do is you have to sort of draw down to the correct answer. Okay. Could I have done this? Could I have drawn a secant from here to here and just brought the point in that way? Could I have done that on the other side? You see what I'm saying? So I did this on the right? So I brought in a point on the right and brought it down and kept getting closer and closer to the right tangent. Could I do it on the other side? Yes. Okay. And the tangent's only really going to exist if I could do that. So what I could do, just like before, when we could inscribe the polygon or circumscribe the polygon, here too, we could build the tangents down like this, or the tangent approximation down like this, or we could build it down like this. Okay? And those two things should agree if there's an actual tangent there. So again, what's the lesson here? We want the instantaneous velocity. We want the slope of the tangent. We can't figure that out immediately, so what do? We build an approximation, and we bring that approximation closer and closer and closer to the true tangent and to the true slope. Okay? The derivative is calculus's answer to the general tangent problem. And that thing that we did here is exactly how we find the derivative. So the way we're going to develop the derivative soon enough in this course is going to be exactly along those lines. Okay, these are two problems that seem different, right? The area problem and the tangent problem seem substantially different. Okay, they seem to have nothing to do with each other, and yet we solved them in similar-ish ways, right? We built approximations, we refined the approximations, and we saw where that sequence of approximations took us, right? And the place that a sequence of approximations takes us, or converges to, is called the limit. And the limit is what the two branches of calculus are built on. And there is yet another connection between the integral and the derivative. And again, these seem unrelated, right? The problem of area and the problems of tangents. But in the final weeks of this course, we're going to talk about a theorem that brings them together, okay? That unifies these two things and gives us a really beautiful connection between two things you didn't expect to be related, but are related, and it's a very, very useful theorem. Two beautiful things coming together. It's not a spoiler. It's not a spoiler. That's from 4 years ago. I was careful. That's it. Next class we're going to be talking about functions, and again we have lecture and we have tutorial on Monday. If you've got any questions at all, either ask them now or come up to the front. Have a wonderful weekend. Be happy, be safe. I'll see you on Monday.